So this is just going to be a quick example, and I decided to record it at home because we probably are about a day behind. But this is a short lecture, so we're not even a full day behind, but I thought it would be best to be all caught up by Monday, so I thought I'd record this little example to sort of round out chapter 12, the transfer function chapter. So here's the problem. It's pretty straightforward. So let's find the matrix transfer function h of s for the state model shown. The state model has, as always, an A, B, C, and D matrix. It is missing a dot on the x, which I'm sure you already noticed. Let me just, that works. Okay. So here's our ABCD definition for our state model. Also find the poles and zeros of each scalar transfer function. So those are the two parts to the question. And here's the solution. So the solution that we previously derived for the matrix, the transfer function matrix, is that h of s is equal to the C matrix times quantity S times the identity matrix Si minus A inverse B plus the D matrix, D. So let's plug those matrices in, and of course this is the C matrix, so it's actually just the identity matrix. So it's a 2 by 2 identity matrix, 1 0 0 1 times S times the identity matrix is just going to give us S along the diagonal, 0 0 S minus the A matrix, which from here is just 0 1 negative 4 negative 4. And we're going to be taking the inverse of that matrix, multiplying it by the B matrix, which is 0 1 and then adding the D matrix, which is 0 0. So notice this is coming back to this is a single input. U is a single quantity, a scalar, and multiple output. How many outputs? That's right, I heard you. 2 outputs. Excellent work. So let's go ahead and use the next line to continue. The inverse that we'll need to compute is of this matrix. The identity matrix essentially just dissolves away, has no effect, so we can just drop it. The first term of the matrix we need to invert is S minus 0. Second term is 0 minus 1, so negative 1. Third term is 0 minus negative 4, or positive 4. Last term is S minus negative 4, which is S plus 4. We need to invert this. And then we're going to be multiplying it by the B matrix still, which is just 0, 1. And the D matrix, the plus 0, has no effect, so we can just drop that. So let's just go ahead and write that. Recall that the inverse of a 2 by 2 is pretty straightforward. One thing we need to do is to take the determinant of this matrix and write it in the denominator of this expression, 1 over that. So the determinant is s times s plus 4 minus -1 times 4, which is plus 4. So it's s squared plus s plus 4. It's the determinant. Multiply it by these two terms switched, so you have s plus 4 and s, and then terms, the signs change like this. And did I do that right? I did. Look at me go. Times 0, 1. Okay. And let's write that on the next line. 1 over. You may have noticed that we could factor this expression in the denominator. This is just s plus 2 squared. And that is multiplying s plus 4 times 0, or 0. 1 times 1 is 1, so 1. And we have -4 times 0 is 0, and s times 1 is 1, or sorry, is s. So that is what's left of this matrix multiplication. And really, this is our answer. It's pretty simplified at this point. So I will go ahead and say this is our h of s. And that, as you see, is the matrix transfer function. So each term here is descriptive of a scalar transfer function between the one input that we have and the output that is associated with that term. So the transfer function 1 over s plus 2 squared, that takes inputs u to outputs y1. And this transfer function, s divided by s plus 2 squared, that transfer function describes the relationship between the input, the single input we have, and y2, our second output. So those are our two transfer functions. The 1 component of h of s, as I said, is the transfer function from u to y1, and the 2 component, like I just said, is the transfer function from u to y2. So that's convenient. So we have both of those. So let's go ahead, and we're also asked to identify the poles and zeros of each scalar transfer function. So let's go ahead and do that. We know that both, they always have, so always when you have a matrix transfer function, all of the scalar transfer functions have the same poles. So both have the same poles. My screen is a little laggy tonight. That's why my handwriting looks really bad, but what do you do? So those poles are found by, it's whenever the denominator is 0, right? The denominator is the same for both of these transfer functions. It's s plus 2 squared. So to find out where those poles are exactly, we can just say s plus 2 squared equals 0. And let's solve for s to find out when this is the case. So that implies, and we're going to just immediately write this as pole 1 and pole 2. I think by inspection we can recognize that s is equal to -2 is actually the solution, and there are two of them because this is squared. So there are two -2's. So we have a double pole, it's called. Double pole. And notice that it's real, right? It's a real double pole. Okay. The only zero that's in this, so when I look at the zeros, we need to know when the numerator goes to 0. Well, the numerator of the transfer function between u and y1 is 1. And no matter how you change s, 1 never becomes 0. Therefore, we have no zeros, or 0 zeros, which I think is rather fun to say. So, the only 0 is in the second transfer function, which can be found by setting that numerator equal to 0 and solving for s. Well, that is simply just setting s equal to 0 and solving for the values of s that satisfy this equation, which, by golly, are just zero. So the 0 is, I call it Z2. I'm just going to call it Z. There's only one 0. So Z is equal to 0. And we can do a pole 0 plot for each of these. So for the first transfer function from u to y1, we have the two poles, right? And they show up at -2. So we often write the double pole with this fancy little x. And no zeros, so there's no zeros. The second transfer function has the same poles, right? It has to be the same poles. And it also has a 0 that occurs at z equals 0. So we put the 0 there. That's probably a little large, but yeah, put the 0 there. And that is all there is to it, our pole 0 plot. I mean, let's think about it for just a moment. We have both of the transfer functions have all the poles in the left half plane, right? Therefore, the system is stable. Good job. And the fact that it's a double root actually implies that we have critical damping. And, excuse me. So that means that zeta is equal to 1 for this case. So that is our second order system interpretation in terms of the parameters. Yeah, so critical damping, double root, stable. Yeah, that's about it. We have 1 0 here. We haven't learned enough to interpret what that 1 0 at the origin means, but in time we will understand that a little bit better. So that's really it for tonight. Niles is asleep, otherwise I would come introduce him to you. This is my cool, well, this way. This is my cool artwork from my friend Dan. He makes really cool art. It's like 3D thread art. Anyways, so that's what's been like behind my head all night. So that's all I really needed to show you guys. Yeah, and if you have any questions, you can ask me in class on Monday. So yeah, have a good weekend. I'm really enjoying mine. I got a massage today. So yeah, so far, the day after, the Friday before the rest of my life, it's been pretty good. It's been really nice. So hope you guys are also enjoying your weekends, and I'll see you on Monday. Take care.